Hi everyone! So in today's video, we're going to use implicit differentiation to prove some new derivative rules. So specifically, we'll be learning derivative rules for some inverse trigonometric functions. Before we get started on that, I just wanted to remind you all that right now there is a survey I have open that you can basically just give me feedback on how the class is going for you so far. So there are questions about, how is the pacing of the class? How does the amount of homework feel? Stuff like that, as well as just, asking if you have any specific feedback. So I can't promise that I'm going to be able to address every single thing that people want to see changed, but it really helps me just get kind of a general feel for how people are feeling about the class. So that's in the week 6 module at the top, and I will be taking that down probably definitely by the end of this week, just because I don't want it to be like a semester or quarter long thing. It's really just for me to kind of check in the middle of the quarter to see how things are going so that I can make adjustments while we still have time left in the quarter. So one thing I just wanted to specifically address, just because someone mentioned, it's completely anonymous, by the way, and so I don't know who posted this, but someone said how they wish that the specific homework questions for each day were listed, and I just wanted to show you that that they are, and maybe this person was referring to the fact that there's definitely been a few times where I've been a little behind on posting it, but I just want to make sure that you all know that it is here. So if you click on the week 6 summary or whatever week it is, there's a schedule that says kind of what section of the book we're covering each day, as well as the homework questions that you should be able to do after watching the lecture for that day. So some weeks I've definitely fallen a little behind on posting which homework questions there are. This week I made sure to kind of get it all done at the beginning, but just wanted to address that in case there was anyone else who wasn't aware of that. Okay, so before we get started, so this is still technically section 3.5 in the book. So we're going to be talking about derivatives of inverse trigonometric functions. That's not how you spell it. Trigonometric functions. So before we get into actually taking the derivatives, I just want to do a very quick review on how inverse trigonometric functions work, because it will help us to be able to kind of understand how we come up with their derivatives. So this is a quick review. So basically, when I say inverse trigonometric functions, we're talking about things like y is equal to inverse sine of x. So I'm not talking about the reciprocal trig functions. So that would be things like 1 over sine, 1 over cosine, 1 over tangent. The inverse trig functions are very different from the reciprocal trig functions. So how do inverse trig functions work? Well, basically, if you have a normal trig function, so let's say, f of x is equal to sine of x, you plug in an angle, and then the output is a ratio, right? It's a number between -1 and 1. So the way the inverse trig works is that you plug in a number between -1 and 1, and the result, the output, is an angle. So it's reversed. Regular trig, you plug in an angle, out comes a number. Inverse trig, you plug in a number, out comes an angle. So when I write down right here, I said y is equal to sine or inverse sine of x. That is equivalent to, actually, let me say it this way. I think this might be a little clearer way to phrase it. So I'm going to say if y is equal to inverse sine of x, then that is equivalent to saying that sine of y is equal to x. So whatever number is inside of the parentheses in an inverse trig function, that's the result of taking that same regular trig function of that number. And then there's one other thing to add here, which is that there's kind of this restriction put on with inverse trig. And we'll do a concrete example in a second. If there's too many variables floating around here, we'll make it a lot clearer with a specific example in a moment. But whenever you're taking inverse sine of a number, there's only specific angles that are allowed to come out. It's kind of built into the definition of these inverse trig functions is this restriction. So specifically, whatever number you get here, so y, so that's the result of taking inverse sine of a number, right? That's an angle. Y has to be in the interval from negative pi over 2 to pi over 2. So basically what's going on here, let's look at a concrete example. Let's say that you wanted to take inverse sine of 1/2. So what are you looking for? You're looking for an angle, and specifically, you're looking for the angle so that if you take sine of that angle, you get 1/2. But additionally, that angle has to be in this interval. So let me draw a quick sketch of the unit circle here to help us figure this out. So when you're doing inverse sine, you're specifically looking for angles that are in this part of the unit circle. You're looking for angles that are either from 0 to pi over 2 or 0 to negative pi over 2. So what is the angle in that range that has sine equal to 1/2? Well, if we go to an angle of pi over 6, right? So an angle of pi over 6 has coordinates of square root of 3 over 2 and 1/2. And so because the y coordinate is 1/2, that's what tells us that sine of pi over 6 is 1/2. So inverse sine of 1/2 is equal to pi over 6. And the reason for that is because sine of pi over 6 is equal to 1/2. And additionally, because pi over 6 is in the right part of the unit circle, it's in the right interval of angles. So just to give kind of a counterexample, it would not be true. So we could find a different angle on the unit circle that also has an x coordinate of 1/2. So for example, if we go to this angle here, so this would be an angle of 5 pi over 6. It is true that sine of 5 pi over 6 is equal to 1/2, but it's not true that inverse sine of 1/2 is equal to 5 pi over 6. And the reason for that is because inverse sine is specifically kind of restricted to only give you particular angles as your answer. And so because this angle, 5 pi over 6, is not in the correct part of the unit circle, it's not allowed to be the answer for inverse sine of 1/2. So inverse sine of 1/2 is just pi over 6. There's only one answer, even though there are many, many different angles that you can take sine of them and get 1/2. There's only one that's the correct answer for inverse sine. So these specifics aren't really going to come up too much in this class. Maybe let me just write that sentence down. Because 5 pi over 6 is not in negative pi over 2 to pi over 2. So these specifics are not really going to come up in the class, but I just wanted to mention them because the one thing that is going to come up is basically understanding this first sentence that I wrote down in blue. So understanding that if you have a number equal to inverse sine of x, that means that sine of that number is equal to x. And also it means that that angle should have been in that particular interval. I just want to write down similarly the definitions for inverse tangent and inverse cosine because they actually, so inverse cosine has a different restriction for the types of angles that comes out. So I just want to make sure you're aware of that. So if y is equal to inverse cosine of x, that means that cosine of y is equal to x, and y is now not in the interval from negative pi over 2 to pi over 2, but from 0 to pi. And then for tangent, or inverse tangent, so same idea. So if y is equal to inverse tangent of x, that means that tangent of y is equal to x. And it also means that y has to be now in the interval from negative pi over 2 to pi over 2, but not including the endpoints. And the reason for that is because tangent of pi over 2 is undefined. So I know this is a very quick review. This is something that you should have learned in your pre-calculus class, and I covered it pretty recently in my pre-calculus class that I'm teaching right now. So if you go and look at my YouTube videos, you should be able to find my 142 videos, that's pre-calculus 2, and there's a few videos about inverse trigonometry. So if you're feeling a little rusty and you want to brush up on it, then I would recommend checking those out. Okay, so why are we talking about this? Well, we'll see that it's going to come up when we try to figure out what the derivatives are of inverse trigonometric functions. Because what we're going to do is we're going to, instead of trying to find the derivative when it's in this form, which we can't really do because we don't know what the derivative of inverse sine is, right? We haven't learned that rule yet. But we do know what the derivative of sine is, right? So what we're going to do instead is focus on writing it in this form, and then we can use implicit differentiation. So we're going to do that, and that will tell us what the derivative, or that will allow us to eventually figure out what the derivative of inverse sine is. Okay, so we're going to finding the derivatives of inverse trig function. So again, this is going to be like pretty much a proof. So I always like to just say up front, you don't need to completely follow every step of the proof in order to use these rules, right? So once we get to the end, it will be very clear what the derivative rule is. And then if you didn't understand all of this, that's okay. You can just kind of take that derivative rule in hand and move forward with it. But I like to show where it comes from, especially because then if you forget it, it's not actually that hard to kind of recover what that derivative is if you understand where it came from. Okay, so the first thing that we're going to do, so we're going to start by finding the derivative of inverse sine. So we're going to, in this video, do inverse sine and inverse tangent, and then I'm going to ask you on your worksheet to try to figure out inverse cosine yourself. And it's going to be very similar to how these ones go. Okay, so how are we going to do this? So we're going to start by writing down a function. So let's say that our function is y is equal to inverse sine of x. So as we saw on the other page, this is really equivalent to saying that sine of y is equal to x, and with that added restriction that y is an angle that is between negative pi over 2 and pi over 2. Okay, so we're going to use implicit differentiation and we're going to use it on sine of y is equal to x. So we're going to take the derivative of both sides. And compared to a lot of the other implicit differentiation questions we've done lately, this one is pretty easy. So the derivative of sine of y is going to be cosine of y times y prime. And then the derivative of x is just 1. And so if we solve this for y prime, we get y prime is equal to 1 over cosine of y. Okay, so from here, this is in some ways a valid derivative. However, because our original, so if you think back to like the examples we were doing in the previous videos, the reason we were using implicit differentiation was because they weren't functions, right? They were kind of, the x's and y's were blended together in a way that they couldn't be separated. And that's not really the case here. Because our original statement was a function of x, y is equal to inverse sine of x, that is a function. Because it's a function, we should be able to find a way to rewrite our derivative as a function of x. So because our original function is, I mean, I'm being kind of redundant here, but it's a function of x. I guess I could say curve to be like a more general term, but because our original function is a function of x, its derivative can be expressed, and we just have to figure out how, as a function of x. So how are we going to do this? Well, let's look at like what's kind of our key? What's the thing that allows us to go back and forth between y and x? So if we look back to kind of what's the clearest relationship we can find between y and x, it's this, right? This is we can think of this as our key for translating between x and y. So if we're trying to get our function to have an x in it instead of a y the way it does here, we probably want to, instead of having cosine here, if we can rewrite it as something involving sine, that will then allow us to replace it with an x, right? We don't know that cosine of y is equal to x, but we know that sine of y is equal to x. So if we can find a way to rewrite cosine of y so that there's no more cosine, but it's written as something involving sine instead, that will allow us to then kind of make that translation back to x. So what are we going to use here? So we need to, basically what we're saying here, we need to translate this to sine of y so that we can then translate it to x. So what's the relationship between cosine and sine of an input? Well, there's a nice identity that relates cosine and sine, and that identity is cosine squared of any input, I'll just say y since that's what we're dealing with here, plus sine squared of that same input is equal to 1. So that's what's called the Pythagorean identity. And that's really important, I think, of all of the different, I can't spell right now, Pythagorean, of all the different identities that you learn in pre-calculus. I think this is maybe the most important one. Because how can we use this? Well, if we're trying to translate cosine into sines, if we can solve this for cosine, that will give us cosine in terms of sine. So if we subtract sine squared of y from both sides, we're left with cosine squared of y is equal to 1 minus sine squared of y. And so that tells us that cosine of y is equal to the square root, and actually, sorry, there's one thing that we need to put here. It's equal to plus or minus square root of 1 minus sine squared y. And why is there a plus or minus? Well, anytime you're solving something, like just to give a total side example, if you're solving like x squared is equal to 4, that means that x is equal to plus or minus 2, right? So there's always that possibility of plus or minus. And so that's where this is coming from. However, we can actually kind of narrow this down because we know something about y. So remember, we originally said that our angle y has to be in this interval. So if y is in that interval, if y is between negative pi over 2 and pi over 2, so let's think about what that looks like. So that means that y is an angle that is in this part of the unit circle. So if we're in that part of the unit circle, cosine is always going to be positive because cosine is the x coordinate of the terminal point when you're on the unit circle. So if the angle that you started with is in this part of the unit circle, then cosine is guaranteed to be positive. And so going back to what we had down here, we can basically say, okay, this has to be the positive one. And the reason for that is because y is in the interval from negative pi over 2 to pi over 2. So cosine of y has to be greater than or equal to 0. Okay, so what can we do now? So now we can take our equation up here and rewrite it as y prime is equal to 1 over 1 minus sine squared of y. And then we can go back to our key up here. So our key told us that sine of y is equal to x. And so instead of writing sine squared of y, using that key that we had up there, oops, sorry, I forgot something. There's supposed to be a square root here, right? So this was cosine of y is equal to square root of 1 minus sine squared of y. So because sine of y is equal to x, we can then replace that part with an x. So we're left with 1 minus x squared. So again, I know that was kind of complicated. There's a lot of different steps there, but at the end of the day, the important thing to know is that we have a new derivative rule. So that new derivative rule tells us that the derivative of inverse sine of x is equal to 1 over the square root of 1 minus x squared. Okay, so I want to do the same thing for inverse tangent, and it's actually a little easier. There's a little bit less involved with it. So let's do that one real quick, and then like I said, on your worksheet, I ask you to do the same thing for inverse cosine. And the inverse cosine one is very, very similar to this one. So then once we know what the derivative of inverse tangent is, then we'll do some examples of basically like, now that we have this new derivative rule, using it together with things like the product rule, the chain rule, the quotient rule, things like that. Okay, so one more example, and maybe I'll just do this on the same page actually. So let's now do the derivative of inverse tangent of x. So for this one, again, we want to start with this kind of statement. We want to say y is equal to inverse tangent of x, and our goal is going to be to find y prime. So if we rewrite this as x is equal to, or maybe to be consistent with how I wrote in the last one, tangent of y is equal to x. And then we have that extra kind of information that says that y is in the interval from negative pi over 2 to pi over 2, not including the endpoints. That part doesn't really matter to this. Okay, so we're going to take the derivative using implicit differentiation for the second thing that we wrote down, so this part, tangent of y is equal to x. Okay, so what's the derivative of tangent? In general, it's secant squared. So in this case, we're going to get secant squared of y times y prime, right? Because we're doing implicit differentiation. And then we get 1 on the right-hand side. And so we're left with y prime is equal to 1 over secant squared of y. So again, we need to eventually translate this back in terms of x. And so again, we're going to go back to this kind of key. And so in this case, we need to figure out a way to go not from, not the last one we were trying to go from, I think what, cosine to sine, right? Yeah, cosine to sine. And so this one we want to go from secant to tangent because it's tangent that will allow us to kind of translate stuff back in terms of x. So there's another Pythagorean identity that you can get from the same one that we wrote at the top. So we're going to, we need to translate this to basically tangent. So we wrote down this Pythagorean identity above, which said cosine squared of y plus sine squared of y is equal to 1. And so really when it comes to Pythagorean identities, and by the way, this stuff of using Pythagorean identities and kind of being able to translate between different trig functions actually comes up a lot in Calc 2. So it's kind of, that's part of the reason that I'm doing these proofs, is because I think it's good to kind of remind yourself about some of this stuff before you get to Calc 2. So this is the first Pythagorean identity. The nice thing is that if you know this Pythagorean identity, you can get two other ones just by dividing everything in this equation by the same thing. So in this case, we want a Pythagorean identity that relates secant and tangent. So if I go through and I divide everything in this equation by cosine squared of y, which you're allowed to do, right? We're just doing the same thing to both sides of an equation. So that gives us 1 plus tangent squared of y is equal to secant squared of y. So that's another Pythagorean identity. But again, you don't really have to memorize that as its own thing, because if you know the cosine squared plus sine squared equals 1, you can always just kind of derive it yourself. Okay, so this is great because secant squared of y is exactly what we have, right? So now we can go back to our derivative and say y prime is equal to 1 over 1 plus tangent squared of y. Because originally we had secant squared of y, and we just figured out that secant squared of y is the same as 1 plus tangent squared of y. And then we can go back to that key. So we had that key that told us that tangent of y is the same as x. And so we can rewrite this as 1 over 1 plus x squared. So the derivative of inverse tangent is equal to 1 over 1 plus x squared. All right, so now that we have these new derivative rules in hand, I basically just want to do a couple of examples, just like practicing using them together with some other derivative rules. So examples. So let's start with this one. So inverse sine of 5x. So let me actually I'll write down the two rules that we found on the other page here, since you probably don't already have them memorized. So we found on the other page that the derivative of inverse sine was 1 over the square root of 1 minus x squared. And we found that the derivative of inverse tangent is 1 over 1 plus x squared. So we can refer to these as needed. Okay, so this one is a chain rule problem, right? Because our input is not just x, it's 5x. And so we need to apply the chain rule and kind of take the derivative of the outside, leaving 5x as our input, and then we'll multiply by the derivative of 5x. So that outer part of the derivative is basically just going to be taking this derivative rule here, and instead of putting an x, we'll put a 5x. So we have 1 over the square root of 1 minus 5x squared. So that's the outside part of the derivative. And then we need to multiply by the inside part of the derivative, which is just the derivative of 5x. And so the derivative of 5x is 5. So that will give us f prime of x is equal to 5 over the square root of 1 minus 25x squared. And I would definitely recommend, this is one of those videos where, because we're just doing, I think we'll do like 3 more examples, I would definitely recommend pausing and just trying them yourself and then coming back together if you know, to check in whether you got it right. Okay, so next one I want to do is x squared, so let's call our function g of x, is equal to x squared times inverse tangent of x. So this one is going to be a product rule, right? So we're going to use, for one of our functions, we'll have to use this second rule, and then the other function is just x squared. So our derivative is going to be taking the derivative of our first part, so that gives us 2x, and multiplying that with inverse tangent of x. And then we'll, to that, add the derivative of inverse tangent, so that's 1 over 1 plus x squared, and then we're just multiplying that with x squared. So altogether we get 2x inverse tangent of x plus x squared over 1 plus x squared. And that's it. And a lot of these derivatives are not going to look super simple just because in some cases stuff will kind of simplify, but a lot of the time, because these are kind of like complicated looking derivatives and involve fractions, don't be too surprised if your final answer still doesn't look that simple, even after you kind of do everything you can to try to make it look simpler. All right, a couple more. So let's do -3, so h of x is equal to -3 times inverse tangent of square root of x. So because we're just multiplying by -3, as usual, we can just kind of like keep that on the outside and multiply in at the end. So we can even just do something like this, say -3 times, and then we'll kind of deal with whatever's going on with inverse tangent. So for the inverse tangent part, we have to use the chain rule, right? Because it's not just inverse tangent of x, it's inverse tangent of square root of x. So the first part of the derivative is going to be using this inverse tangent derivative here, but we're going to be replacing x with square root of x. So instead of it being 1 plus 1 over x squared, it'll be 1 plus 1 over 1 over 1 plus square root of x squared. Write that a little more neatly. So 1 plus square root of x squared. And then we have to multiply by the inside derivative. So the inside derivative is going to be the derivative of square root of x. So hopefully at this point we've done this one a lot, and I think it's a good one to kind of commit to memory. After you use the power rule and then simplify, you should get 1 over 2 times the square root of x. Okay, so this one we can do a little bit of simplification. So we end up with -3 times, so this first one is 1 over 1 plus x now, right? Because the square root of x squared gives you x. And then here we have 1 over 2 root x. And so now we can just kind of multiply all this stuff together. So we're going to get -3 in the numerator. And then the denominator, and thought I was doing a good job in this video of keeping things level, but it's fallen apart a little bit. In the denominator, we'll have 1 plus x times 2 square root of x. And we can distribute that. So we end up with -3 over 2 root x plus 2x root x. And that's it. All right, one more example. So let's look at the function y is equal to 1 over inverse sine of x. So there's a couple different ways to do this. You could use the quotient rule, or you could use the chain rule. And I'm not exactly sure which one's going to be easier off the top of my head. The nice thing about using the quotient rule on something like this is that the derivative of the numerator is 0, right? So there's not going to be as much going on. That being said, I generally kind of find that the chain rule is a little easier. But maybe in this case, let's go with the quotient rule. I think that will end up being a little easier in this case. So the quotient rule says we take the derivative of the numerator first. So the derivative of 1 is just 0. And so we don't even really care about what else is here, but I'll just still write it so that we kind of know where it came from. So we had 0, so the derivative of the top times the bottom, and then we're going to take the derivative of the bottom. So that's 1 over square root of 1 plus x squared, 1 minus x squared. And then we divide that by the denominator squared. So if we put this together, it's going to be 1 over the square root of 1 minus x squared divided by inverse sine of x squared. And then rather than have a fraction within a fraction, so this is the same thing as 1 over the square root of 1 minus x squared times 1 over inverse sine of x squared. And so we can just rewrite it as just one fraction. So we can write this as 1 over square root of 1 minus x squared times inverse sine of x squared. And you should get the same thing if you do the chain rule, and you can almost like see where the pieces come from. So if you were to use the chain rule here, you would want to rewrite your original function, and this is going to be kind of confusing looking, but if you were to rewrite this function as inverse sine y is equal to inverse sine of x to the -1. And the reason I'm saying this is confusing is because these two -1s mean totally different things. This -1 means inverse, like an inverse function, whereas this -1 means to the -1 power. So it looks like you're kind of doing the same thing twice, but it's actually like completely different meanings. So if you were to use the chain rule, you would end up with, basically that's the chain, if you use the chain rule, doing the outside derivative is where you would get this part from. And then this part comes from the inside derivative, the derivative of inverse sine. So I would encourage you to try that if you want to kind of verify for yourself that it comes out the same. That would be a fun thing to try. All right, so that is it for today. So there will be some more examples for you to try on today's worksheet. And yeah, that's it. See you next time.